You're here because you want to master kinetic particle theory with a University of Cambridge graduate. Let's begin. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Before we begin, be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. So we've already learned how our solids, liquids and gases are different states and how they actually behave from our lower levels. For example, right, we know that solids are fixed volume, right? They have fixed shape, they cannot be compressed, and they generally do not flow. Versus our liquids, they generally have a fixed volume, but they don't have a fixed shape. They also cannot be compressed, but they flow easily. And then our gases, right? They, in contrast, have no fixed volume, no fixed shape, and they can be compressed and they flow in all directions. Now, the kinetic particle theory is a new theory that you will learn, and this says that all matter actually consists of particles that are too small to be directly visible, and these particles are always in a constant state of random motion, right, at varying speeds. So with that in mind, right, we know that any molecule or compound or atom, right, they actually exist in particles, right, and these particles, right, have different kinds of constitution, and they behave differently in actually different states. For example, our solids, right, they are actually closely packed in an orderly arrangement. They have very strong attractive forces between the different particles, and they have very high density. And most importantly is the movement. They actually vibrate about its fixed positions. So it's actually very important to answer all these key criteria when you're encountering a kinetic particle theory question that asks about the movement of particles or how they behave in their different states. So this is for a solid. For a liquid, right, the particles are actually loosely packed in a disorderly arrangement. Alright, they still have very strong attractive forces, just not as strong as a solid, right? And still have a very high density, again, not as high as a solid, but still high. And the particles are, instead of vibrating about fixed positions, since they're more loosely packed, right, you can imagine the particles are sliding over one another freely. Now, how does this compare to a gas? Gases, right, these are more far apart and have more random arrangement for the particles, okay? And this is more expected because you know that they don't really have a fixed shape or a fixed volume, so the particles are definitely more and more far apart. And then for attractive forces, this is definitely the weakest, okay? For a gas compared to a solid or liquid, these attractive forces are weaker between the particles. And for density wise, it's the lowest density. And for the particles movement, they move about at high speeds randomly. In terms of energy level, right, the energy level of the particles actually increases from a solid to a liquid to a gas. So please bear that in mind. Another thing we must know are the processes which the states will interchange between itself. For example, we know that a liquid generally evaporates or it boils, okay, to a gas. And we know a gas would condense to become a liquid. Our liquids are also known to be able to freeze, okay, to form a solid. And our solids are, in contrast, able to melt to form the liquid. Now, something that we probably can learn is how a solid becomes a gas. Solids can actually become gases by subliming. And gases can actually also become solids by deposition. So this is a rather new concept. So what are some of our common substances that we actually can see doing sublimation? For example, we have iodine. Iodine is actually this dark purple solid at room temperature, and because it has a relatively low boiling point, right, when you actually apply low heat, this iodine solid, right, can actually become this violet gas. We also have another example called dry ice. This one you've probably seen in public before. Dry ice is frequently used as a cooling agent, and it's useful in keeping temperatures low. And instead of normal ice, it actually sublimes to form gaseous carbon dioxide instead. And this is rather useful again as a cooling agent. You can see it usually used at events itself. Now, the last concept you need to understand about kinetic particle theory is diffusion. Diffusion is the movement of molecules from a region of higher concentration to a lower concentration. And this happens all the way until all the particles are mixed evenly, or in other words, equilibrium is achieved. And during diffusion, alright, how this works is that the gas or liquid particles, right, they will move to available spaces in a container, and this is through random motion until everything is mixed thoroughly. So what are some applications of our diffusion? For example, we have the spread of perfume. So this actually kind of explains why you're able to smell a perfume all the way from another corner of a room, right, if you're all in the same room together. This also explains why you can smell cooking aromas when you're not in the kitchen itself. These molecules that help you smell these cooking aromas, right, are actually diffusing from the kitchen itself all the way to your nose, right, from a region of high concentration to a region of lower concentration. So what are some of your factors that can affect the rate of diffusion? And this is actually really important because this is very commonly tested in your exams. Number one, you have molecular mass. So if the molecule weighs heavier, or the particle weighs heavier, then the rate of diffusion for the particle would be slower, which kind of makes sense. Heavier things generally take more effort to travel. The second factor is temperature. The higher the temperature, the higher the kinetic energy of the particles, and therefore the particles will have a higher speed, and thus you will generally have a higher rate of diffusion. So over here you can see this diagram shows how diffusion actually works. If you have a high concentration of a particle in a particular region, right, it will actually diffuse naturally, and the particles will travel in random directions all the way until your particles are very evenly distributed. In other words, equilibrium is achieved. If you enjoyed today's video, do remember to click the subscribe button so that you can enjoy more free content from us and improve your chemistry with us together. If you want to join my community of students to learn more secret formulas to acing chemistry, do check us out in the link below and sign up for a free trial class today.